In subtopic D.3 we looked at the cosmic scale factor. We're going to come back to that in this video, but before we do we need to have a look in a little bit more detail at the idea of the density of the universe. We're going to do that by referring to the density parameter, which has the symbol of omega naught, and the density parameter of the universe is basically just a ratio, and it's a fairly straightforward ratio, and it's the ratio of the average density of the universe to the critical density. So you can express it fairly simply as the equation that omega naught is equal to rho over rho c. So basically we're looking at whether the critical density is equal to, greater than, or less than. And so if we consider it now in terms of the density parameter, we'd identify that if omega naught is equal to 1, then the universe is flat. And when we talk about the universe being flat, just to expand on this idea a little bit more, what we're really saying is that gravity is strong enough to prevent the universe running away. By running away we mean just sort of expanding uncontrollably. So it's strong enough to prevent that sort of the runaway universe, but it's not strong enough to pull it back in. So we won't see it sort of coming back in on itself. So flat universe can still expand, but won't actually sort of collapse back in on itself. Now, if omega naught is greater than 1, so we're then saying that the density of the universe is greater than the critical density, then the universe is going to be closed. And again, considering this in terms of gravity, gravity in this scenario is able to pull the universe back in. So it's strong enough that it will eventually pull the universe back in, and we consider that the term that's often used for that is the Big Crunch. So we've got the Big Bang being the start, and if the universe is closed, then we'll end up with a Big Crunch. Finally then, if omega naught is less than 1, then we're going to see that the universe is open, and here gravity is too weak to prevent the universe running away. So they're the three scenarios, again in a different interpretation or a different level of detail. And with that in mind, we'll now come back and have a look at the cosmic scale factor. Just incidentally here, by the way, observations of the universe and measurements that you can take would suggest that the value of omega naught is about 1.00 plus or minus 0.02. So it kind of looks like it's flat, but there is still that uncertainty there that it could still be either open or closed as well. If we consider the cosmic scale factor, and the idea behind the cosmic scale factor here, you can think of it as sort of relating to the size, or sort of in inverted commas, the radius of the universe. Considering how r has changed over time, the easiest way to have a look at that is by considering a graph. And rather than annotate this graph, we'll just sort of have a look at what is represented there. So you can see that our place in the universe is represented by now, or our place in time, and you can see that we have all of these lines intersecting. So, and the reason for that is that's what we can currently observe, and all of them, you can see there the value of r is increasing, so it shows that the universe is expanding. Now, if the universe was closed, so we'll start off with omega naught being greater than 1, what we would expect to see is that the universe would eventually collapse back on itself, and that means that the universe will have some definite endpoint. It also means that it has a starting point that's actually a little bit earlier than the other models that we might consider. Now, if it's a flat universe, you can see that the starting point was a little bit earlier again, so 10 billion years before now, and then the universe would continue to expand, so gravity not able to pull the universe back in. For an open universe, you can see that the expansion continues, and so this line actually sort of starts to curve a little bit up above the flat universe. You'll notice that we've also got this line representing the accelerated universe. So the accelerated universe is basically indicating that the expansion could be increasing and sort of really uncontrolled expansion. It's possibly just explained by dark energy, and it's something that we'll get to later in this particular unit. Now, the other thing to consider with the cosmic scale factor is the effect on temperature. So we've seen the wavelength of radiation from a galaxy so taking this sort of, now we've talked about the cosmic scale factor with respect to time. Now let's have a look at it with respect to temperature. So the wavelength of radiation from a galaxy is in line with the cosmic scale factor. And by in line, we mean that as the cosmic scale factor increases, so does the wavelength. So as R increases, so does lambda. And we can also then tie that back into Wien's law. We saw from Wien's law, so when we consider black body radiation, we know that there is a relationship between the maximum wavelength and the temperature, and that relationship is that the temperature is inversely proportional to the maximum wavelength. So from Wien's law, we've got that relationship, and so we can then relate that back to the cosmic scale factor, and we can identify then that T is also inversely proportional to the cosmic scale factor. So in other words, as the cosmic scale factor increases, as the size of the universe increases, the temperature of the universe will also decrease. What this then kind of leads us to is that continued expansion of the universe, so we're now not talking about a closed universe, continued expansion of the universe would lead to the big freeze. So because the size of the universe continuing to increase, the temperature will continue to decrease. In keeping with the whole Big Bang, Big Crunch kind of idea, we have the big freeze here. So the temperature of the universe would decrease to lower and lower values. So eventually, you're kind of looking at everything just becoming too cold, and the universe would effectively just die out. So there's some interesting aspects to do with the cosmic scale factor.